Hi and welcome back to Module 8, and today we're looking at video 4 and we're looking at NMR, so nuclear magnetic resonance. So what is this? Let's have a look. Now, the outcome on our syllabus that we are hoping to achieve is to investigate the processes used to analyse the structure of simple organic compounds addressed in this course, including but not limited to using proton and carbon 13 NMR. Now, this is a little bit more tricky than we have seen with IR and also mass spectroscopy. The theories behind them are a little bit tricky, but once we become a little bit more familiar with analysing the spectra, I'm sure you'll find it okay. We just might need a little bit more time in class to practice. So let's get started. So a nuclear magnetic resonance is basically a tool that is making use of the magnetic properties of the atom, and in particular the atomic nucleus. And it helps us determine the physical and the chemical properties of the molecules that we're studying. So just a little bit of background information with this. I'll just move again down out of the way. Our NMR spectroscopy uses our electromagnetic radiation, similar to some of the other types of techniques that we have looked at recently, but in this case they're using radio frequency. So we're using that longer end of the spectrum, so where the wavelengths are really quite long, the wavelengths are quite long and therefore the frequency is also quite low. So because the frequency there and they're too low, they don't cause much vibration like we needed with IR and so forth. So to be able to use these radio waves, we have to introduce something called nuclear spin. Now, in our previous unit, we did look at spin before in our Year 11 unit where we looked at spin up, spin down and pairing of that spin. Well, we're going to do the same here with our protons and our neutrons. So for this to happen, we have paired particles. Now, if they're paired up, they cancel each other out and therefore won't have nuclear spin. So what we need the nucleus to have is some unpaired protons and neutrons there for us to get that nuclear spin. So if we look at the case of carbon-12, there are 6 protons and 6 neutrons in the nucleus, so they're paired up, there is no spin. So really only nuclei that have an odd number of nucleons, so protons and neutrons, will actually possess spin that will create a magnetic field. And this is a property that NMR is based on. We're looking at things such as a proton, so hydrogen 1, carbon 13, so they're the two we are going to study, but you can also see phosphorus 31, and there are some other ones that will also have that unpaired nucleon. So here we have some isotopes, and you can see here where some of the spin is a little bit different. So in the case of hydrogen 1, the spin a half, hydrogen 2 spin of 1. If you look at carbon 13, again a spin of a half. If you look at phosphorus 31, a spin of a half. So there's those similar patterns there that we have that can be useful in this technical analysis technique. So let's have a look. Let's look at spin. So when we put some matter in a nuclear field, basically they're acting like mini bar magnets. So if you imagine a compass, when we align a compass, it has a spin, it spins around and it faces towards north. So they're like little compass needles, and when we have them within Earth's magnetic field, then they all point towards north. So any charged particle there will develop that magnetic field. So the atoms of these isotopes will be magnetic here. So let's have a look a little bit more. If we place a small magnet in a large magnetic field, like our compass, it'll move. So if we place our nuclei in a strong magnetic field, they're all going to line up like our compass needle, like our bar magnets. So they'll tend to either point in the direction of the magnetic field or against the magnetic field. And it's this property that's going to be our big feature of NMR. So if they are aligned with the magnetic field, they have a lower energy. If they're aligned against the field, they have a higher energy there. So the difference between the higher energy and the lower energy spin states will depend on what type of nucleus it is and the chemical environment that's surrounding the nucleus. And again, that's what we're going to be looking at, the chemical environment there surrounding that nucleus. So what happens is, to induce a higher magnetic field, a radio transmitter is actually used to flip the electrons the protons and neutrons into a high energy state, so against the field. So this magnetic radiation is applied, the magnetic field is flipped against the magnetic field alignment, and they're in a higher energy state. Over time, they will flip back into their regular low energy alignment, and they will be releasing the energy they absorbed as they do so. And this releases a pulse of energy, and it's this pulse of energy that we're actually seeing on our... So what happens in an NMR? Now, I don't know that we need to know a lot about this in terms of our exam, but it certainly helps us understand what's going on and the theory behind what we're actually seeing. So when we pop a sample into a strong external, so that's in our NMR with the radio frequencies being applied, we can measure the absorbed frequencies of radiation and get information about what's happening in that nucleus. So in theory, every hydrogen should produce a consistent output, as should every carbon-13. However, that doesn't actually happen because there's a number of shielding effects that happen within the atom as well. So magnetic fields will vary between different atoms because we've got electrons also that have got spin around the outside, providing a shielding effect to the nucleus from that external field that we have there. So here on the right we have the basics of what happens in the NMR. So we have got a sample being placed in, it's exposed to a magnetic field through a powerful electromagnet. Remember at the TAFE the man was talking about the NMR and how strong the magnet was, that the tradesman's wrench couldn't be removed and it was just standing there in that field. So it goes through there, we have the radio frequency generator, and then we have it detected on our spectrum that we can then see. So different atoms will have different environments, even different hydrogens within our molecules will be in a different environment and therefore give off a different pulse, and we will look at these in further videos. So the two different types of NMR, as we've stated before, that we are going to look at is our proton NMR, so hydrogen NMR, hydrogen 1, and also carbon-13. So we're going to be looking at carbons, very useful for organic, and the hydrogens that surround them, also useful in organic. And that'll give us some information that we can use also in conjunction with IR and mass spec to tell us about what the compound might be. Talk about this a little bit more in class C then. NMR spectrum.